And so I want to encourage you to get started on those homeworks earlier rather than waiting until the last minute so that you have time to email me if you have questions or get together with each other to work together. Waiting till the day they're due, you can run into problems. And so the pro tip is to get ahead of me in ALEKS. I know a lot of times you think, oh, I haven't seen that problem in class yet, so I'm going to skip it or whatever. Or I want to wait till the end so I know that he's covered everything. But if I cover something that you don't know yet in class, sometimes it confuses you, right? And then you go for 2 days not thinking about it, and then you see it in ALEKS, and you're still confused because you can't remember what I said about it 2 days ago. Is that typical? I mean, that's the way I remember school. It's like the professor would talk about something, and I didn't quite understand the vocabulary he was using or the thinking that he was using. And then I would go try the homework 2 or 3 days later, and I couldn't remember what was said in class. So that's a real difficult way to learn, and that's what makes college so hard. Okay, if you get ahead of me, and this works in any class, if you get ahead of the professor by trying the homework before they've covered it in class, then you're putting the vocabulary in your head with a lot of question marks. You've seen terms, you've tried to use things that you don't quite know if you're using them right. Then you get to class and the lights come on. So you've already kind of explored the room in the dark, and you get to class and lights are coming on, and you're like, oh, I can't wait to get back to the computer so I can enter my answers and do it the right way. Okay? So that's the pro tip for all of college, every class, is try to get ahead of, read ahead. Do a little bit more work before you're ready to do it so that when you get to class, the lights come on and then it clicks. Okay, so this is a little pro tip, and it'll absolutely work. That's when I started making A's when I was in school. I did not start out great. Okay, so what we're doing today is this middle part of homework B. The Monday video lecture will finish it out. Okay, you don't have to wait till Monday. Once I haven't recorded it yet. But once I get it posted this afternoon, then you can go in there and start working on it. You can probably do it yourself too, just reading the explanations, but I'll have a little video working on these last 4 topics. Okay, so let's talk about empirical formulas. This one actually was one of the more confusing problems in ALEKS. Like when I was reading it, it took me 2 or 3 times to read the instructions to figure out what is it they're even asking. And I know what an empirical formula is and what a molecular formula is. So sometimes, even though you know what the science, it's trying to read their problem and figure out what they're asking. Okay. So what they're wanting us to do is, first of all, just look at these molecules and come up with a molecular formula. That's pretty easy, right? However many carbons we have, it's like C5. And how many hydrogens? Maybe it's H10 and so on. So we can make the molecular formulas real easy. This whole group thing is something we'll explain in a second. So let's do the molecular formula for the first one. So we look at it, very simple. We just add up the carbons, right? 1, 2, 3. So we've got C3, and then add up the hydrogens next. 1, 2, 3, 4, 5, 6. So there's 6 of those. And then the oxygens, there's 3 of those. So it's that simple for the molecular formula. The point I want to make is you can only make a molecular formula if you know the molecule. That makes sense, doesn't it, right? It's a molecular formula. If you don't know the molecule, you can't make the molecular formula. Sometimes when we take an unknown substance and we put it in an experiment, we can only get the relative proportions of carbon, hydrogen, and oxygen. And since that's the old school lab trying to find out what stuff is made out of, we stick it in there, we'll burn it, and then we'll collect the CO2, and that'll tell us how much carbon is in there. We'll collect the water, and that'll tell us how much hydrogen is in there, and then the balance of that will be the oxygen. So we can get a CHO analysis, but it only tells us the relative proportions of those. So that experiment would only give us the empirical formula. Can you see up there how I got the empirical formula? What did I do? Yeah, divided everything by 3. So that's the empirical formula is the simplest ratio of all the different atoms. Okay, And that's what I would get out of this combustion analysis. If I burned this molecule, I'm destroying the molecule, but I still get the relative amounts of carbon, hydrogen, and oxygen by weighing out the water, the CO2, and then doing a difference to get the oxygen. So the empirical formula, empirical means experiment. You can think of it as experimental formula, but we call it the empirical formula. And it's related to that carbon, hydrogen, oxygen analysis experiment. So it's old school, 1800s, okay? But the concept of the empirical formula is still really valid. It's the smallest common denominator of all of the, you divide out by the smallest common denominator of all of the different types of atoms. Okay, so by definition, the first one we do is going to be in group 1. So, you know, let's say we had a whole shelf of molecules. We had these 4 molecules in different jars, and we did this empirical formula analysis. We did this carbon, hydrogen, oxygen analysis. We would be able to put the molecules in groups, but we couldn't really tell what the molecules were from that CHO analysis. Okay, so this next one, we add up the carbons. There's 4 of them. There's 4 hydrogens and 4 oxygens. So that's C4H4O4 for that molecule. If we did this combustion analysis, we would only get the relative proportions, and what would it be? It'd be CHO. So we would divide all of those by 4, and we get CHO as the empirical formula. And ALEKS is just saying, if it's not the same as group 1, then put it in a different group. So this would be group 2. So I would go down in the drop-down box and say, this isn't the same as the one above it, so we're just going to call it group 2. Okay, so that's it. Okay. All right, molecule number 3. I count up the carbons, 4 of them, 4 hydrogens, 4 oxygens. So that's my molecular formula. And notice you can have different molecules at the same molecular formula. Okay. Simplest form of that would be CHO. And so then this now is saying, we got to pick. Is it in group 1? No. Group 2? Yes, it's in group 2. So I'd use the drop-down box and pick group 2 for that one, because it's the same as the one above it. Okay. And then this last one, I go around and count the carbons. There's 5 of those. There's 10 hydrogens and 5 oxygens. So I'm going to end up with this molecular formula, C5H10O5. If I divide everything by 5, I get the simplest ratio of CH2O again. And so then that's going to be in group 1. So I look at my other options. It matches group 1. Let's say it came out as something totally different that didn't match group 1 or group 2, then I would just pick group 3. So you may have some of those on ALEKS. You may have one where all 4 of them are different. And so it would be group 1, group 2, group 3, group 4. And you may have one where all 4 of them are the same, and it would just be group 1, group 1, group 1, group 1. So that's how you answer this kind of question in ALEKS. Okay, so, but does everybody understand the difference between the empirical formula and the molecular formula? That's the science that we're trying to teach here. Okay. In the lab in the 1800s, we would get the empirical formula, but we didn't know what the molecule was. So we could classify things based on their empirical formulas. And in fact, if we took sugar and starch and cellulose and ran it through, think how different those things are. Sugar, starch, cellulose. Ran it through our different experiments, through this carbon, hydrogen, oxygen analysis experiment, we get the same empirical formula. You know what that empirical formula is for those? What are the terms for starch, cellulose, and sugar? The classification, if you're looking at your nutrition facts. Carbohydrates. What's their empirical formula? CH2O, carbohydrate. Yeah, that's where it comes from. So carbohydrate is the empirical formula for starch, for sugar, for cellulose. It's pretty cool, okay? And so that's like a real world example where we have the empirical formula. All of those substances have the same empirical formula, but they have very different molecules. Like a sugar molecule is different enough from a cellulose molecule that I can use the sugar molecule for fuel, and I can't use the cellulose molecule for fuel. Last chance for questions on this. Anything? Okay. Now, let's start talking about naming and making compounds. So there's a lot of different ways to make compounds. We have the nonmetals up there in the upper right-hand corner of the periodic table, and we can make compounds with those, like carbon dioxide and so on. And they have a certain naming scheme. And then our salts, metals and nonmetals, react together, and those have a different naming scheme. So for the next 2 weeks, a week and a half, it's just going to be learning all the rules about naming. So there's going to be a lot of little rules, and you're just going to have to learn by doing and do more and more problems. So let's focus on the nonmetal covalent molecular compounds. So I'm using the word covalent as opposed to ionic. So covalent, they're sharing the electrons. Ionic, one is stealing the electron from the other to make charged particles. So in this case, we've got molecules or atoms that are sharing the electrons. And that's what neither one of the nonmetals wants an electron more than the other, to the point where it would actually ionize that atom and steal it completely. So here's the explanation for these kinds of compounds. And notice for like N2O5, we've got a nitrogen and an oxygen, but we've got two nitrogens. And so we're going to use that prefix di. So this will be dinitrogen. And then we have 5 oxygens. So we're going to use the prefix pent, pentoxide. Now, a lot of the molecules have common names like water. I mean, you could do water like dihydrogen monoxide, but it's so common that we just call it water. And ammonia, NH3, so that would be trihydrogen nitride, I guess, but we just call it ammonia, NH3. So there's a few common molecules that we use. But here's our compound prefixes for these non-metal compounds, these covalent compounds. So there's really no substitution for memorizing these. It's up to 10. We're not going to go higher than that. But, penta is 5, tetra is 4, hepta is 7. So just become familiar with these. And again, you become familiar with these by using them and naming a bunch of different compounds. So this is how we tell the difference between PCl3 and PCl5. These are two common forms of phosphorus and chlorine as they react with each other. And so PCl3 is phosphorus trichloride. PCl5 is phosphorus pentachloride. Notice that penta has an A on the end, so does tetra. And so these ones that end in a vowel, there's a little bit of a nuance in how we use them with oxide or things that start with a vowel. So notice down here, carbon tetrachloride, 4 is tetra, and so we keep that A, but whenever the element begins with a vowel, like if the prefixing ending in O or A is used with an element name that begins with an O, like oxide, we drop the O, like mono, or A, like tetra, from the prefix. And so notice there's a missing A down here. So osmium, OSO4, would be osmium tetroxide, not tetraoxide. And so that's just the scheme, that's the way it is. So they don't have those two vowels next to each other. Makes it difficult to say. So that's osmium tetroxide. So here's a whole bunch. Nitrogen's a great molecule to practice on because you have all these different forms of nitrogen in nature. You have nitrogen monoxide, NO. That's what the joke was at the beginning. The teacher said, do you know the molecular formula of nitrogen monoxide? And the student said, no. And she said, very good. He's like, what did I do? Nitrogen dioxide, dinitrogen trioxide, and then dinitrogen monoxide. So it should be mono, but it begins in oxide begins with an O, and so we drop one of the O's. So it's monoxide. So let's practice. So here in ALEKS, we have these different molecules that they've given us. So silicon dioxide. So we got to find silicon up there. Where's that? It's Si. It's right below carbon. Okay. So we have carbon dioxide. We also have silicon dioxide. Okay. So that'd be SiO2. And then boron monophosphide. So sometimes you need to look at this and say, well, what's the element and what's the ending? So notice all of these are ending in IDE. And so we need to find this PHOSPH, phosp. Okay, well that's phosphorus, so that's P. Okay, so this is BP. Sounds like a gas company. Okay, then dibromine monoxide. So we've got two bromines, Br, and an oxygen. So BrO2. And then we have silicon dioxide. Or no, we have sulfur dioxide, so SO2. So, yeah. So whenever there's the first element is just a single one, we don't do monosulfur dioxide. If it's the first element, we just say sulfur dioxide. Then over here we have triphosphorus pentanitride. And so now we have the A on penta because nitride doesn't start with a vowel, so we keep that A. And so we've got tri is 3. What is penta?
5.
Yeah, good. 5. And so we have P3N5. Here we have diphosphorus. The whole word's written out for us, so we don't have to really think about that. So di is 2, and tetra is 4. Okay, so it's P2O4. Oh, I screwed that up, didn't I? There's a copy paste there, I think. So ignore my mistake. That should be a 4. All right, then we have phosphorus triiodide. So there's just one phosphorus and 3 iodines. And then this one is diphosphorus tetraiodide. So tetra again is 4. So we have 4 of those. So Pi3, P2I4. So these nonmetals can make a lot of crazy different compounds, okay, with each other because there's a lot of different ways to share those electrons. So you can have phosphorus share 3 electrons and have a lone pair. You can have phosphorus share 5 electrons. There's a lot of different things that they can do. Okay, so these covalent compounds, the nonmetals, the chemistry is pretty crazy. Nitrogen and oxygen have all kinds of different forms that they make. Any questions on this? This one I would say is the entry level, pretty easy because you're given the name, and all you got to do is match it to the elements on the periodic table. So you got to know what bromide and iodide and things like that are. But it's pretty easy because it says di or tri or tetra, and you can figure it out. It's when you're given the formula and you've got to figure out what the name is. That's a little more tricky. You're going to be given all kinds of formulas, and one of the things you need to know is, do these little prefixes apply? So is it a molecular compound? Is it a nonmetal situation where I've got to use di and tri and tetra, or is it some other kind of situation? So this is another set of problems, predicting if a compound is ionic or molecular. We just did the molecular naming rules. So if it's ionic, we're going to have a different set of rules. So this is one of the skills we need to make sure we're good with. Like you look at a compound, you're like, is this an ionic compound or a molecular compound? And it's pretty simple. If the compound's made up only of nonmetals, it's a molecular compound. If it's a metal and a nonmetal combined, then it's ionic. Okay. So Ba, Br. So we've got barium. Tell me if barium's a metal or a nonmetal. Metal. Yep. And this is a nonmetal. So let's say that a metal equals M and a nonmetal equals N. Okay, so this first one's going to be ionic because you have a metal combined with a nonmetal. What about this one? I'm looking at carbon. Metal or nonmetal? Right, so I'm going to put an N by that. And then sulfur, nonmetal. So I've got two nonmetals bonded to each other. So that's going to be a molecular. Okay, so that's a molecular. Hydrogen, nonmetal. And sulfur, nonmetal. So that's going to be molecular. But wait, hydrogen is in group 1. It's unique, right? Even though it's group 1, it has one valence electron, but it's not a metal. Okay, so that would be a molecular compound, H2S. Let's do it again. Okay. Whoa, this is weird. Lead, I got that one. It's over on the right. You see it's at element 82. It's right below carbon. But that diagonal line, that separates metals and nonmetals. And so it's below that diagonal line, so it's a metal. Okay. And then this crazy thing. We haven't learned our polyatomic cations yet, or anions, but this is acetate. Okay. But I can look in there, I can see carbons and hydrogens and oxygens. Those are all nonmetals. So this is acetate, so that's a nonmetal. So this is going to be an ionic compound because it's a metal and a nonmetal bonded together or associated with each other. Boron monophosphide, definitely molecular. And then hydrogen fluoride, so a gas, a hydrogen and a fluorine, both nonmetals, so that's molecular. So again, this is how we would decide which naming scheme to use. So we would call this, let's do it. What is the name of CS2? Carbon disulfide. Carbon disulfide. Okay? But this one is not barium dibromide. We use a different naming scheme for that because it's ionic. Okay? So this is just barium bromide because there's only one kind of barium bromide. Okay. So barium always makes a +2 cation, bromine always makes a -1 anion, and so you need 2 of those always for the barium. And so this is why I'm saying we got to know if it's ionic or molecular, because if you call this barium dibromide, you get it wrong. Okay, it's not the name of that compound. So you got to find the molecular ones, and that's the ones you use the di and tri and so on. So this would be dihydrogen sulfide. Dihydrogen sulfide. This one over here, boron monophosphide, and this is hydrogen fluoride. It's also hydrofluoric acid if you put it in water. So. Let's do one more. This one, a little strange. We've got aluminum. That's a metal. Okay, and this is chromate. Very good. It's an oxoanion. But anyway, we've got oxygen in there, which is a nonmetal, and we've got a metal here. But the point is, we got metals and nonmetals in this compound, so it's going to be ionic. Okay, so we're going to call that one ionic. This next one is molecular. Okay, dihydrogen carbonate. We don't know how to. You don't know that yet, but we will know that later. Okay, and then this last one, you got nickel, which is a metal, and chlorine, which is a nonmetal, so that's ionic. So the rules we just covered, the di, tri, tetra, they only apply to the moleculars. So if it's a molecular one, then you can use those rules. So that's why I probably wouldn't have done this if I was making up my own notes to teach, and in my notes in the past, I probably wouldn't have emphasized this skill. And that's why I really appreciate ALEKS, because it says, hey, you can teach the naming rules, but if your students don't know the difference between an ionic and a molecular compound, they're not going to know which time to use this rule or that rule. So I really do appreciate the thought that's gone into ALEKS. I know you guys would sometimes get mad at it, but it's making sure that we take baby steps on some of these things, and that's good. Okay, let's create binary ionic compounds. So now that we know metal and a nonmetal makes an ionic compound, how do we determine what the subscripts are going to be? So if we combine these anions and cations, we can make these binary ionic compounds. So the real trick here is that all of the charges have to cancel out. You have to have the same number of positives as you do negatives. And if you do that, then you'll get them all right. So if we're looking at this, I've got magnesium here. I'm trying to find my pen. Okay, here it is. Magnesium 2+. And the fluorine is a -1. So I need 2 of those fluorines. So do you see how this works out? So you've got a 2+ here and a minus there, and that minus is times 2. So the minus on the fluorine is doubled because there's 2 fluorines. So the positives and the negatives cancel out, and I've got a neutral formula. So your formulas have to be neutral to make these ionic formulas. Now for magnesium and sulfur, they both match. So I just need 1 of each atom. So I can have a S2- and an Mg2+. The charges match, so we're good. We don't need any subscripts. So all we're doing is just looking at those charges, and we're trying to make it to where it balances out. Nickel has a 4 positive charge, and so I need 4 of those -1s on the fluorine. So it'd be NiF4, and now everything is canceled out. So it's not, I like it. It's way better than Sudoku. I think that's a dumb thing. Okay, so I can look at this. That's right. It's kind of fun, but the thing that drives me crazy is it's just 81 if-then statements, right? And that's what a computer can do. And so I wrote an Excel sheet that solves Sudoku puzzles because it drives me crazy to like watch myself just do if-then, 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 if-then. But this is if-then too. If the charges don't match, I need more of one of these things here. Okay. So now this next one is a little different. It looks like, well, no, it's okay. So I've got a +4 on the nickel. Each of the sulfurs is a -2. Okay, so times 2, that gives me a -4. So I've got -4 and +4, they all match out. Okay. So the next one, this one's got a nice little twist to it on the last one. Okay. So you might be getting bored with the plot here. We got to match the charges. So zinc is a 2+, the boron's a 1-, so we need 2 of those bromines. I said boron, but I meant bromine. Zinc is 2+, sulfur is 2-, same thing, ZnS. Okay. Now gold is 3+, and bromine is a -1, so we need 3 bromides. But this is the one that kind of tricks people. It's not hard, but 2, 3, yeah. So the way this works, if you think about it, is we've got to get the 3 and the 2 to match. And so we got to multiply both of them. So this is a 3+, and this is a 2-. And so this whole thing gives a -6, and this whole thing gives a +6. So this is the way it works with all of these 3 2s. Okay, so let's look at another 3 2 that's really common. Iron oxide, Fe3+, O2-. Okay, and so what we have whenever we have these 3+ and 2- is you have this nice little thing, they crisscross. So the 2 comes down here and the 3 goes over here. So Fe2O3 is the way to work that. Or Au2S3. Or what about aluminum oxide? So aluminum, we also have this a lot. 3+ for the aluminum, oxygen 2-. So we do that crisscross. This is Al2. Why did I write a 3? Al2. Let me go. O3. So that's a nice little pattern that you see frequently in coming up with these little subscripts. You like this one? This one's pretty straightforward. Y'all should be able to like hammer through this one and move on to the next topic. Okay, so now we get to the naming part, naming the binary ionic compounds. It's always a metal and a nonmetal. We're going to combine them and we're going to name them. And we've got quite a few rules on this. Okay, so cobalt and bromine, we have 2+ on the cobalt and a -1 on the bromine. So it's COBr2. But we don't really know how to name it yet, but we can make the formulas. Okay, let's go through the explanation in ALEKS on the naming. Okay. So then we've already established that the net charge on the whole thing ought to be 0. And that's what we just did, those last two problems. It was combining the positives and negatives so that their charge was 0. Okay. And so then we can repeat that with the other compounds. So this is COBr3, 3 plus and a Br minus. Okay. Potassium bromide is KBr, and magnesium bromide is MgBr2. So we just more practice on making those formulas. If you can get those marked down. Let's get into the names. Okay, so in naming the compounds, they have the cation name and the anion name. And if the cation is an atomic ion or metal element, then the name is just the name of that metal, like sodium or potassium or whatever, or even iron. Okay, but sometimes you have to have some Roman numerals in there if it's unclear. Like sodium always just forms a +1 cation because it's in this first column. Same with potassium, lithium, rubidium, cesium. So we don't ever need, there's no ambiguity with those. There's no uncertainty with those. They're going to always be +1. But when you get to iron, iron can be a +2 sometimes and a +3 other times. So we need to use a Roman numeral to tell the person we're communicating with which compound we have, because it's about communication. If you write iron oxide and you send that to me, I don't know which one you're talking about. Is it iron 2 oxide or iron 3 oxide? Because I don't know if your iron is +2 or +3. So we've got to communicate. That's what the whole naming thing is about. It's not just trivia. It's about communication. So sodium, no question. All sodium ions are going to be Na+. Calcium, no question. They're all going to be 2+ because it's in column 2. Same with strontium or barium or magnesium or beryllium. Okay, but when we get to iron, you have two different types of iron: iron 3+ or 3+ or 2+. So you put this Roman numeral in there when you name it. Okay. So the green squares, we don't need Roman numerals. The only one I question is maybe manganese, but certainly these others, you don't need Roman numerals for any of those green ones. So that's really nice. So it probably just makes sense to learn the non-green ones, right? And these are going to be the only elements that we really talk about in detail, So chromium, 3+ and 6+. And you're just going to have to know it's a 3+ and a 6+ for chromium, okay? You could make a chromium 4 or something like that, but these are the most common in nature. So this is what you're going to come across. It's chromium 3 or chromium 6. Chromium 6 is the one that's carcinogenic. So we're trying to remove chrome 6 from all of our chrome plating processes. We love to chrome plate stuff to make it last longer. But if our process is using chrome 6, then we have a cancer risk to our workers. Aaron Brockovich movie was about that. Iron 2 and 3, copper 1 and 2. So it's kind of random, right? Copper's 1 and 2, but iron's 2 and 3. So, and then this one, gold 1 and 3. This is the crazy one, and we'll talk about that. This one is, we'll talk more about mercury, but mercury's weird. This is mercury 1 and 2. It looks like a 2+ and a 2+, and it is, but this has 2 mercury atoms in it. And so each one is charged 1+. And so this is mercury 1 and mercury 2. So here are all the ones on that sheet that have multiple options. So chromium 3 and 6. And we use Roman numerals. Did they teach Roman numerals in K through 12 for you guys? You did? It's probably school to school, right? And so we're not going to get into the like MX, MLC, and all of that business like they do in the ends of movies. Sometimes they'll have it in Roman numerals, and I'm like, when was that made? And I'm trying to figure it out. But we'll go up to like 6. Chrome 6. It's VI. Okay. And so that's V is 5, 1 is 6, I is 6, I is 1, and so 5 and 1 is 6. And then you have iron 2 and 3, copper 1 and 2, gold 1 and 3, mercury 2. So look at that, mercury 2, mercury atom with a 2+ on it. But look at this one, it has a subscript. It's the only polyatomic cation on this list. So there's multiple atoms in this thing. And so there's 2 mercury atoms, and the whole thing is charged 2 plus. So each mercury atom is only charged 1. That's why this is mercury 1. So that one catches people. Okay. So I'm glad you're here today. so this is the mercury 1 ion. It's charged 2 plus, but there's 2 mercury atoms. And this is the mercury 2 cation. That's like next level. Okay, so then the rules for the anions. We got the metal part. Now let's do the non-metal part. Okay, if it's just an atomic ion off the periodic table, like oxide or fluoride, then we just take everything after the first syllable, we remove it and put IDE on the end. So fluorine becomes fluoride, and chlorine becomes chloride. Oxygen has 3 syllables, but we just take everything after that first syllable and put "ide" on there, so it becomes oxide. It's not oxygide, it's oxide. Okay. So everything after the first syllable is gone, and then I like that way better. When I learned it, it was the root. They said it's the root plus "ide," but I never know what the root was. Okay. But it's very, very clear definition to say everything after the first syllable. So the first syllable is the root. Okay. So now we can name these compounds. And we've got bromides. All of them are bromides. And we just need to know when we need to use the Roman numerals. And so for the cobalt, we need to use the Roman numerals. So that's cobalt 2 bromide, and that's different than cobalt 3 bromide. And you can see that the molecular formulas are different. So there's a chemical difference between these two. They're both in the group of cobalt bromides, but one is cobalt 2 bromide and the other is cobalt 3 bromide. Then there's no Roman numeral needed for the potassium bromide because the potassium's in group 1. It's always going to be a +1 cation. And the same with magnesium bromide. There's no ambiguity or uncertainty about magnesium because it's in group 2. Always going to be a 2+. I feel like you've been following me, but I want you to pause and ask yourself, do I really understand this? Is there anything I could clarify for you? Because we've gone real fast. We ran right through those rules, and you're like, yeah, it makes sense, but does it?
So when we're writing out the name of the compound, does anything need to be capitalized?
No, it does not. There's a tendency to want to do that, and I do it too sometimes and mess up, but it doesn't have to be capitalized. They're not formal names.
Okay.
Yeah. Yes.
So going off of that, if you do capitalize it, will we get like a penalty or anything?
Well, in my exams are multiple choice, so there won't be any problem there. ALEKS, I don't know. I don't think so, but I don't know. Does anybody have any experience with getting it right, but it was capitalized and getting it counted wrong?
I think it tells you.
It'll tell you.
Oh, it will. Okay. So that'll add a little. Does it count it wrong, or does it let you correct it?
It'll count it right, but it'll put a note. Like if you put in a decimal and just put .006,
Okay.
Oh, yeah.
it'll tell you it's right, but usually we put 0.006.
Oh, that's a great
Yeah, still
example.
counting.
Yeah, that's good. I like that because I remember from ALEKS in the past that if you missed one, then you got extra ones to do. Is that the way? Is that only on the knowledge check, or is that going on right now?
No, it's through the homework.
That's for the mastery part. You got to get it. Is it 3 times in a row to master it?
Yeah, some are 3, some are 5.
Oh,
So if you get
okay.
it 2 times in a row on a 3-question block, you'll go on to the next.
Okay.
Or
Okay.
3 times in a row. But if
Okay.
you get 2 times in a row and then you miss one, it'll knock you back 1.
Yeah. Okay.
Because you get an extra point for if it's in a row.
Okay. That's how it's
You have
working.
to do 5 total.
5
but-
points.
Yeah, but you get extra points.
Yeah, if it's a sequence and you nail it.
Yes,
Yeah. That's why I'm hesitant for someone to try to do it, capitalize it, even if you know, but then it knocks you back, right?
It
So,
allows you to make it better.
okay, yeah, okay.
And if you if you already have one right and you hit the explanation,
Mm-hmm.
it won't give you that extra point. It'll just start you over. You'll get one
Yeah.
correct, and if you get another one correct, you'll get 2 extra points.
Okay. So on the explanations, does it make sense to just do the explanation on the first one if it's a new problem?
Yeah, if you don't know yet.
Yeah, if you really don't
Or
know.
do a couple of them.
Yeah, yeah, and so I would appreciate if you, like I'm saying, try to get ahead of me. I mean, you're going to have to do the explanations if you're ahead of me, because I'm essentially doing the explanations in class with a little extra. But if you want to work ahead, then on that first new problem, maybe do the explanation first, and then get that notebook out and take notes in your notebook, that little composition book or spiral, because then as you're doing multiple ones of the same kind of problem, you can look at your notes. There's such a tendency to just, if it's on the computer, to not use anything else. And that's not smart. I mean, you want to take down the math, and so then you get to the next ALEKS problem. It's the same kind of problem. You can look at your notes and see how to do that one, and then do it again. Okay, so that's my suggestion. Okay, let's look at more anions. Just go down. I did every one of the nonmetals here. So carbon is carbide, nitrogen is nitride, oxygen is oxide, fluoride, phosphorus. Phosphorus is a little strange because where does that first syllable end? It takes it all the way to the end of the pH. So it's phosp. You know, I would probably, if I was just brand new to chemistry, I probably would have put phosphide, PHOS, right? But you include that second pH. So it's phosphide, okay? Sulfide, chloride. The selenium is the only exception on the first syllable rule. So it's selenide, not cellide, right? So that's why I put exception here, because you keep the first two syllables on selenium. That's the only one that's the exception. Okay. And then iodide. So that's everybody right there in the upper right-hand corner of the periodic table. So we're making binary ionic compounds with all of the metals. So look at how many metals there are. Everything from this diagonal to the left, you can make with those anions and use this same naming rule. Okay. So it's not infinite combination, but it feels like it. Okay. There's a lot of them. Okay. So that's good. Let's go to your questions, and let's practice. Let me give you some good ones. Okay. Okay. And so we'll do this like the test. I'm writing an exam question for you. Okay, name this compound. A. Okay, don't answer. It takes me a while to write out. Okay, so don't say anything. Okay, so this is going to be B. Okay. I got to come up with bad answers, right? That's part of the fun of being a professor. Okay. C, not B. Dinitrogen 4 oxide is the last one. Okay. So which one is it? So this is the kind of thing that I'll be putting on the test. Okay. So 33 questions. You're like, man, 33 questions in 50 minutes. You know, I got to really make some time. But you ought to be able to come up and look at this question and go, yeah, it isn't that. This is a mess, right? I don't have the tetra here. Okay. I've got a Roman numeral with the non-metal, okay? And so when I'm analyzing people's results and I'm looking at the tests and I'm saying, man, the student's really struggling, and I look at some of their answers and they've circled this one. I'm like, how could they have done ALEKS, right? And come to class and still circle one that has so many things wrong with it. Okay, so So it's fun to make up crazy answers, but it's not fun when someone selects it. Okay, so this is the one you want. It's dinitrogen tetroxide. So. And I dropped the A, the tetra, but I dropped the A because the oxygen starts with an O. All right, y'all have a great time. Weekend and enjoy a little time next week just doing the videos.